gentlemen, I'm pleased to welcome you here at the Technical Forum of the Group Exhibit Hydrogen Fuel Cells and Batteries in Hanover 2014. Come in, enjoy with me the next presentation dealing with the topic Make the Best of the Sun, Meeting Thermal and Electrical Energy Demands. And your presentator is the R&D Manager from Next Energy, Dr. Benedikt Hanke. Give him a big hand, please.
Thank you, Mrs. Lasner, for the great introduction, and welcome to all of you to my presentation. Thank you very much for your interest, and thanks for coming. I will give you a short introduction on Next Energy and where we are doing research and what we're doing research about. A little introduction on what's new on our energy systems in buildings and how energy flows are going to change within the next couple of years. The availability of photovoltaics, probably you know most of it, but let's go into some details there. Energy efficiency and photovoltaic probability, how that goes hand in hand. How do we get the electrical energy storage done, and then let's talk about some thermal potential and what that might end up with combinations on CHP systems. So Next Energy is based in Oldenburg, which is basically, northwest of Hanover, over to Groningen, in between there. Oldenburg has 30 years of renewable energy research experience. A lot of departments in the university are dealing with the subject, and there's about 250 researchers involved in renewable energy research at Oldenburg at whole. Next Energy is an independent research institute at the Karl Ossietzky University of Oldenburg. We are a non-profit organization with EWE as our main sponsor, and founded in 2007 as a public-private partnership. We have a new building since 2009 with around 2,500 square meters of laboratory infrastructure and about 100 people working there in these three departments. So Next Energy is organized in three departments: one of photovoltaics, one of fuel cells, CHP, and one of energy storage. All have a good base on material research, where we're really looking into the details of the developments there, and then doing the step into the system, taking one step further into how do we integrate all the three technologies into a building. What does that mean for energy flows and for combining single systems? And even one step more up the road, there's the demand for how can we integrate renewable energies into a European grid, and what impacts are there on sizes of cables and demand on energy flows if we go 100% renewable in Europe. So energy systems of buildings, that's the old way. You have some fossil fuel source for your heating, some fossil fuel source for your driving. You have your electrical demand from the grid, case closed. Simple thing. Then in Germany, 10 years ago, we started putting amounts of photovoltaics on the system, and that already started putting new energy flows into our buildings. We now have energy going from the photovoltaic system to the grid, to the consumer, and still coming from the grid to the consumer. Adding storage to the system makes it even more complicated. We have a car that might be there at times or not. We still have the consumers, maybe stationary storage, interaction with the grid, and there's still a couple of errors missing. We might think about grid services from the energy storage to the grid, back and forth, so a lot of options there. Then CHP systems, you all know that better than me. We now have another electrical energy source. We do get a storage tank to get our temperature levels right, and still have some source of gas coming into the house. widely discussed in Germany right now. What do we do if we don't get anything for our photovoltaic energy, if we put it into the grid? So how are we going to work with power to heat systems, especially concerning new homes where the heating demand decreases rapidly with development of new buildings? So overall, there's new components coming into the home to fulfill energy demands, and that includes a whole new complexity of things. So in the classic case, we mostly had 3 forms of energy flow within the building, and with all these new components coming, there's a whole new complexity coming to the home, and we're going to handle that. We need to build efficient overall systems out of single system components in the future and get that all right. So photovoltaics seems to be pretty simple. In the first view, put panels on the roof, inverter in your basement. If the sun shines, you get energy, perfect case. But making it work and getting the money right there has some implication. The first is your location, of course. Here, Germany, south, very preferable. North, less preferable. Then over the year, of course, everybody knows we have winter and summer, and there's a huge difference between radiation during these times. Same thing over different years concerning the same month. We have hot summers like 2006 and cooler summers with even less radiation there. Winter is the same, though there's usually no problem in getting the photovoltaic energy used anyway. So looking at some energy profiles from a PV system. This is 2 years of energy profiles from our PV system at Next Energy plotted above each other, and it's quite chaotic. So there's not really any knowledge of, well, what energy are we going to have at 10 o'clock next day. But I can tell you, okay, during these days to take away the lines and mark every dot that has been reached over that period. And so that gives you quite an area. You can mark the maximum there and see, okay, in any case, we know 2 things. The red area, we know we don't have to consider that point. And the green area, we have to think about. One way of thinking about this area might be to look at the probability. What probability do we have during a day to have a certain amount of energy from our PV system? And at 0.1% of the nominal power, so 1 watt per kilowatt peak, you have quite a good probability, though it's probably not an option to have a PV system that fulfills 1,000 times the energy demand you really need. On other cases, you can turn that graph around and say, okay, here's my daytime, here's the PV power I want to have, and now the probability is the color. Then you can say, okay, if I have an application that runs at 12 o'clock, and I want to run it on 50% probability with full PV supply, or 50%, at least 50% self-sufficiency there, then I'm going to need, 25%. I'm going to have 25% of my PV system, so it needs to be 4 times that large. One way of looking at it. This is the yearly graph. If you have an application that is seasonally dependent, you can say, okay, I have a summer graph. It's obviously much better in the winter graph, where it's really, really bad. We're going to come to that. So if we have a certain probability of having photovoltaics, we can think about, okay, we have certain applications we run at certain times. So what might energy efficiency do to get our self-sufficiency to a higher level? So a good example, I think, is the EU directive on energy demand of vacuum cleaners, because it has certain points we always need to consider. First thing is, you need to fulfill the same job at the same comfort with lower energy demand at the same cost or investment. And all these things happen here. The directive includes how much power is going to be used, but it also includes a label that measures how good the cleaner sucks. So your comfort stays the same at reduced energy demand or power demand and at the same level of comfort. So if we apply that to our to a virtual PV system of, let's say, 4 kilowatts on a yearly probability scale, and at a time frame where the sun is shining between 10 and 12, we end up doing the cleaning job at between 0 and 5% of the times if we use a cleaner of 3,000 watts. If we now use a cleaner of 1,600 watts, it's already 20 to 45% of all times that you fulfill the full cleaning job with only photovoltaic power. And if we go down to these 900 watts at 2017, we are between 35 and 50%. The implication of that is that you need a job where the typical time of use is during the daytime, or we're coming to batteries later. You have a reduced power demand at a constant function, convenience, and investment. Then we come to self-consumption or own consumption versus self-sufficiency. So if your price calculation is based on self-consumption, the 3,000 watt cleaner is much better because you're using all of your PV power you have, and therefore you're earning most of the money. Maybe. So the thinking needs to get right, and you need to put the right priorities on what is your goal anyway with photovoltaics. Coming from energy efficiency, we need to think about what's our energy profile of our home anyway. One good example is this EWE-Forschungszentrum, which is used for CHP system and should be widely known within these circles here. This is a sample day with a minute time resolution for an electrical demand of 4.5 megawatt hours per year. So if you put PV on that, you get about a self-consumption, own consumption of around 25 to 30%. This is basically because, especially in the spring and winter time, there's a lot of lighting applications in the evening and afternoon, mostly when the sun is down. And since daytime is mostly shorter than nighttime, you always have the shifting problem there. So shifting is batteries used here, for example, charging batteries at the beginning of the day, putting it in at night. There's a wide discussion here on, is that the right way to do it? One other way of, you might be able to do it, but then you would need predictions, and there's still a lot of research going on of peak shaving. Of course, there's regulations in Germany that makes you cut your PV power put into the grid to 65% if you own a storage system. So this might be one way of doing it, and also when discharging, what is grid friendly when you discharge? Is it putting your load at a constant load and just shaving your load peaks with your PV system? A lot of discussions going on there. And of course, demand side management. Do you get your wife to really do the cleaning during the daytime and not in the afternoon or early mornings? So when going into money, you need to think about the dimension of your PV system. And using these EWE-Forschungszentrum and the scenario I just showed you, I did a calculation. If you just vary the serviceable storage capacity over time, you end up getting a graph like this. Since it's logarithmic scale, there's a linear increase in self-sufficiency and own consumption up to a certain value, then it flattens, and then it's linear again. So where does it come from? If you divide this energy demand of 4.5 megawatt hours and spread it evenly over the year, which is basically bad assumption, but anyways, you end up having minute reserve here. You end up having an hourly reserve with this regime. Here you have your daily regime. So the bending of the curve starts ahead of 1 day. So if you have a little less than 1 day of average battery capacity, you get the most of it out of it, and then you really start to do investment, and then you get seasonal storage in this part here. So for this scenario, it's around 4 to 5 kilowatt hours for the battery system. Similar, but not as pronounced for the PV. You get something around 4. So putting these two together, we've been just discussing, you get these two nicely colored graphs. So it's got the amount of PV power energy generated on the x-axis, the serviceable storage capacity on the y-axis. And then the conflict between own consumption and self-sufficiency. So from an energetic point of view, there's really no point in optimizing the system. What's your optimization? If you go to 100% own consumption, the best way is to have no PV system at all. That makes you consume all the PV power you produce, which is none, and so there you have your optimum. If you go to 100% self-sufficiency, you end up with a megawatt hour of storage, which is really not, I don't know many people who can pay that from their pocket money right now. So the real optimization must be cost in the future. And then we have to think, okay, where did we start off? We started off with a profile, VDI 4655, which has 10 typical days. We put 2 extra in, summer, cloudy and non-cloudy. So it's based on 12 typical days that are then multiplied to add up to a year. So these curves really hardly depend on the profiles you are going to service with it. So be careful when just taking numbers. If your profile demands a lot of power at night and none at the day, it's going to be totally different than the other way around. Here one example from a field measurement in a home. If you have your oven on and two pots on the stove, you end up having 3 times around 20 kilowatts as a peak, and you need to be careful if you're able to service that or if you need to do that. So then that was the electrical profile. Now coming to a thermal profile. This is a field measurement we do at Next Energy. It has a 2-second interval between measurement points. So you see in light blue the heating demand of the home. It's turned down at night. Then you have the morning peak where you heat up all the rooms that cool down during the night, and then have your normal heating during the day, and then the tap water demand is washing hands, cooking, showering, taking a bath. So the home I said here, it's built in 1997, 100 square meter, 2 adults, 1 child. They have this heating demand. It's 15 megawatt hours of heat compared to 3 megawatt hours of electrical power. Splitting up the heating into tap water and real room heat, you see, okay, it's about 2.5 megawatt hours of tap water and 12 megawatt hours still for keeping the rooms warm. The electrical demand is quite low compared to that. In every month, it's quite constant over the seasons. If you say, okay, we built a PV system that satisfies the yearly electrical demand of my home, and we have a battery system installed that is able to shift the energy within 1 month. So let's look at it in 1 month size and say, okay, the light green, this is what we really want to reach with electrical energy. We want to use it in the electrical way and satisfy electrical demands with electrical energy. So what is left to do heating here? First, we can go into tap water and say, okay, during the summertime, we can satisfy all our tap water needs from photovoltaics if we shift it one-to-one with the heating rod from the electrical to the thermal energy. So then doing heating with photovoltaics leaves you with, in this scenario, 70 kilowatt hours from 12 megawatt hours needed. So that's not really an option. If you then say, okay, then if you want to do heating, we need to produce that energy anyway, so we increase, and I show you, we came from an excess PV energy of 1 megawatt hour that we had to feed into the grid or throw away if feeding in the grid is no option anymore. If we now start increasing the PV power to 1.5, the electrical energy demand we have, we are already back at that value. Because, and if you do it to 2, it doesn't get better. The thing is, in the winter time, we are not even satisfying our electrical energy demands, so we're never going to satisfy our heating demands that are really high during these times. And that's where CHP systems might come in if they get cheap enough to only be run half a year, or if we get regulations that allow sharing energy with the neighbors. Say, okay, I got a neighbor that has CHP system, the other neighbor has a good PV system, and we share energies, thermal and electrical. Who knows? There need to be new concepts for getting this done. So let me conclude, and I'm good in time. Nowadays, the combination of possible home energy system gets quite complex and requires research and development and new tools to do the dimensioning, sizing, putting in of the systems. We can plan photovoltaic use by just using probabilities. It's one way of doing it, or by doing demand-side management and prediction of photovoltaics. Energy efficiency is one important tool to increase self-sufficiency and change the energy demand profile, especially if you're working with batteries. You can live longer on your battery if you reduce your energy demand at night, so lighting is important there. The correct dimensioning of photovoltaic and battery storage system is the key to economic feasibility, and that requires in-depth knowledge of the energy profiles you put down to the calculations. If your assumption on the energy profile is wrong, your business case is going to be difficult. Thermal energy requirements can be utilized to make use of excess photovoltaic energy. If feed-in tariffs drop below gas prices, or if you use heat pumps, and in the winter times we still need alternatives. So thank you very much for your attention, and I'm open to questions.
So now it's on me to say thank you for this kind and very interesting presentation here. Yeah, any questions in the audience right now? Just raise your hand and I will come to you, pick you up with a microphone. Not yet. So if a question or a topic to discuss come a little bit later on your mind, please do not hesitate to visit you and your colleagues at the booth. It's here at the group exhibit Hydrogen Fuel Cells and Batteries, and the booth number is D55. So I think you will welcome everyone there.
Yeah,
okay?
Thank you.
Thank you.
Ms. Lassner.
Okay. Thank you very much. We will continue our program in 5 minutes after a short break with a presentation from the company High Stories. Thank you.